the entirety of that particular wave will be equal to, or the result of that particular waves will be equal to the vector sum of individual waves. So how exactly do we know that two waves are going to interfere constructively or destructively? If light was actually behaving like a particle, the only part that should be illuminated on the back screen was these two parts. So the conditions are basically that the two light sources must emit the same frequency. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about wave optics. So let's see what is remaining for wave optics. So today we will be discussing about what is known as coherent and incoherent addition of waves. But before we are getting into coherent and incoherent addition of waves, we need to remember one small law about vector addition we already discussed. That is, in the first chapter, we learned what is superposition principle in terms of forces. Now we are going to learn about what is superposition principle in terms of waves. So again, what superposition principle states is that at a particular point in a medium, displacement produced by a number of waves will be equal to the vector sum of the displacement produced by the individual waves. That is, if there are multiple waves meeting at a particular point like this, then the entirety of that particular wave will be equal to, or the result of that particular waves will be equal to the vector sum of individual waves. To put it even more simply, we can say that if a wave is traveling like this and another wave is traveling like this, then the output will be a combination of these two waves. That is, these two waves, the very basic nature, that is how the crust is, how the trough is, both will be taken into account and a new wave will emerge having the characteristics of both these waves. That is just a fancy way of putting superposition principle in terms of waves. Now, since superposition principle is out of the way, let's learn what is coherency and incoherency means. So what is coherency? Or simply, what are coherent sources? In one word, we can describe coherency or coherent sources as sources which are having same phase difference, that is, they will be having same or constant phase difference. Same or constant phase difference, and they will be having same frequency also. They will be having same frequency also. For example, if we take the source such as a monochromatic light source or simply a laser, all these are examples for coherent light sources which can actually produce waves. That is, if this is a coherent light source, let's say it is a laser light. So the light or the waves which are coming out of that particular laser light or coherent sources, they will have constant phase difference, or simply we can just say that the phase difference between different waves in that particular source will be constant. The phase difference between two waves emitted by this particular source will be constant. That is, if one wave is traveling like this, then another wave which is emitted by the same source will be traveling at constant phase difference. They will be traveling at constant phase difference. If at one point in time this is the distance between two crusts, then after some point in time or some point in space, this distance will still be maintained. They are not changing that particular phase difference as they travel along. So that particular sources or sources which emit waves that has this particular characteristic, that is constant or same phase difference is known as coherent sources. So what will be incoherent sources? Incoherent sources will be sources which emit waves which do not have constant phase difference, or simply they won't be having a fixed phase difference. With respect to time or with respect to position, their phase difference will actually vary. If at one point in time, if the phase difference is x, then another point in time, the phase difference will be delta x. That is when the wave is traveling after some distance or after t time, the phase difference will be a different value, which means that they are not from a coherent source. So typically, if you want to have examples for sources which produce incoherent beams or incoherent waves, you can say that the sun is a very good example of getting incoherent waves because their phase difference constantly varies. And if you have two sources, for example, if there are two light bulbs or two monochromatic sources, even itself will produce waves which are having phase difference or waves which are having different frequencies also. And yeah, we can call that as multiple sources. So multiple sources will produce waves which are having different phase difference, and sources such as the sun or the white light spectrum will also produce incoherent waves. So why are we studying coherent and incoherent sources? That is because we are going to learn about what happens when one wave which is traveling like this meets with another wave which is traveling like this. What happens when two waves meet each other? So there is only one possibility, that is they will interfere with each other either constructively or destructively. We don't know what happens. So again, before studying about interference, the relevance with coherent sources is that a stable coherent source can actually produce stable interference pattern. Interference means, you have heard people say, right, don't interfere with my matters, don't interfere in my business. Like that, two waves, if they ever interfere with each other, there are two outcomes. That is, either they constructively interfere or they destructively interfere. Again, you know what is constructive and destructive interference. That is, if the crust of a wave and crust of another wave meet together, then they will add up. That is like this, they will add up and they will produce a bigger crust. And if the crust of a wave and the trough of another wave join together, then they will cancel each other out and there will be no wave. For example, if this is a wave and one wave is interfering like this, then the output will be nothing. They will cancel each other out. So that is known as destructive interference. If they are constructively interfering, that is, the crust and the crust will add together and the trough and the trough will add together, then it is known as constructive interference. The wave is enhanced. Otherwise, it is known as destructive interference. These are all topics which you have already learned in your first PUC. So how exactly do we know that two waves are going to interfere constructively or destructively? So the very simple basic thing we can do is measure the phase difference or simply the path length of that particular wave. That particular wave's information will tell us, okay, depending on the path difference, we can actually calculate and say that, okay, will that wave be interfering constructively or will that wave be interfering destructively? So there are two possibilities. One is constructive interference. Constructive interference. And the other possibility is destructive interference. So we have constructive and destructive interference, and we are going to define this in terms of path difference. That is, let's say that there is two sources producing two waves. That is, let's say there is source 1, which is S1, and source 2, which is S2. And these two are producing waves which are meeting at some random point here. Okay, they are meeting at some random point really far away. So again, if two waves are meeting together, then obviously they will interfere. So we are going to find out, is it going to interfere constructively or is it going to interfere destructively? So the very basic thing we can do is understand the path difference of these two waves. And depending on the path difference, we can actually see, is it going to interfere constructively or destructively? If P is the point where they are going to interfere, then we can say that, okay, from the source to that particular point P, the length is S1P and S2P. That is, the path length of that particular wave is S1P and the second wave is S2P. So depending on this, how can you actually calculate what is the path difference? That is, between these two waves, what is the path difference? So again, just like in the first PUC where we learned about waves, we can say that S2P minus S1P will give you the path difference, which is indicated by the letter delta x. Again, x just means its displacement. So to signify path difference also, we are indicating it using delta x. That is it. So again, the path difference S2P minus S1P being delta x, if that particular quantity is equal to n lambda, that is, if it is an even multiple of lambda, then we can say that, okay, this is going to interfere constructively. Or even better, we can define it properly and say that, okay, if the path difference is going to be an even multiple of the wave, then we can actually say that or predict that, okay, it is going to interfere constructively. Both the waves are going to interfere constructively. So again, the condition is that phi, that is, the phase difference should be equal to an even multiple, that is 2n lambda. So this will be equal to, that is, the phase difference will be equal to 2 pi divided by lambda into delta x should be equal to 2n pi. Or simply it is just stating that, okay, the phase difference should be an even value for the constructive interference to happen. Now, what should happen for destructive interference to happen? Obviously, the multiple should be an odd multiple. If the phase difference or simply the path difference is an odd multiple, then we can say that, okay, they are going to interfere destructively, or simply we can write it as S2P minus S1P, if that is equal to 2n minus 1 lambda, that is 2n minus 1 lambda, that is an odd multiple, then we can see that they are going to interfere destructively. So the condition is that, the condition for destructive interference is that 2 pi by lambda into delta x, 2n pi, and here also it is 2n minus 1 into pi. If it is an odd multiple, then automatically it is going to be a destructive interference, and if it is an even multiple, then we can say that it is going to be a constructive interference. Again, the point is that even if you don't understand the equations, the point is that you should know if the path difference or the phase difference is even multiple, then it is going to be a constructive interference, and if it is going to be an odd multiple, then it is going to be a destructive interference. So the very next topic is Young's double slit experiment. So what exactly is Young's double slit experiment? This is actually a reduced portion, but you still have to learn what is the experiment about. That is, you need to know what is the description, but for you to understand the description, you need to identify and know what this experiment was all about. So basically what he did was, there was a light source and he allowed the light source to be passed through a very narrow slit. That is, there were two slits separated by a distance of d, and he allowed light waves to pass through that particular slits. And he placed a screen behind that and observed, okay, what will be the result? So again, the spooky thing is that when light was treated as particles, the all known theories were saying that, okay, since light is passing through one slit, it should be forming one line here. That is, if light was actually a particle, then light passing through this end will only shine that particular point there. And if the light is passing through the other end, then only one more pattern will be found. Which means that if light was actually behaving like a particle, the only part that should be illuminated on the back screen was these two parts. But rather shockingly, when he conducted the experiment, it was proven that, okay, it is not the pattern you're observing. You're actually getting a wavy pattern where the centermost region, that is this particular region behind the screen, getting illuminated more. And it was called as central maximum. And towards the right and left of the central maximum, it was actually gradually decreasing. That is, the interference pattern that was observed was actually stripes of bright light and a dark light, bright light and a dark light, a bright light and a dark light. The result was actually bright and dark fringes which was alternating to both sides, with the center part being illuminated the most. And this result can only be produced if light is behaving like a wave. So you can basically say that Young's double slit experiment actually proved that, okay, light is a wave. But that was actually the spooky thing comes later. That is, so okay, you just proved that light is behaving like a wave. So I'll just see, okay, which part of the slit, that is, he placed an apparatus here which was actually firing electrons or protons, which was actually fired at this particular slit. So the obvious assumption was, okay, if I observe this, if the electron is passing through this slit or this slit, then I have much more clarity. Okay, where is it actually going to land? I'll have that clarity. So what I did was, I placed two detectors here and here, or just one detector also is enough. But the crazy fact was, when this particular detector was placed, light suddenly started to behave like a particle. The spooky phenomena here is that when we are not observing this particular effect, light is behaving like a wave. But when we are actually trying to observe this particular effect, that is, place a detector or something to see which slit the electron or the photon is passing through, then suddenly light is behaving like a particle. Light actually knows if we are observing it or not. Based on that, the result, the output you're getting is varied. So that is actually a very spooky phenomena. But again, here, the only part you have to understand that double slit experiment actually validates the wave nature of light. And the equation in order to find bright fringes is given by n lambda into d by d. And again, in order to find the dark fringe, the equation is 2n minus 1 lambda d by 2d. The difference here is that here n is 0, 1, 2, 3 like that, and here it is just 1, 2, 3. We are not considering 0. In some textbooks, it might be 2n plus 1 here. So the difference is that then the n starts from 0, 1, 2, 3 like that. So here I am only taking 2n minus 1, which means that the n will start from, that is, the numbers start from 1, 2, 3 and so forth. So again, the thing you need to know about this particular experiment is that how this experiment was carried out and what was the result of this particular experiment. That is the description of Thomas Young's double slit experiment. So the description is that Thomas Young demonstrated wave nature of light with this particular experiment. That is, with Young's double slit experiment, Thomas Young demonstrated and proved that light has wave nature. And the second point is that how he done the experiment, what was the parameters, what was the condition of that particular experiment. So a single light source illuminated two very closely placed pinholes which acted as source 1 and source 2 of that particular light. And then one more thing you have to observe is that even though if the light source we used to illuminate those two pinholes were incoherent, after passing through these two slits, that is S1 and S2, they will act as coherent light sources. That is one of the effects of having two very small pinholes. So again, that is just an effect of placing an incoherent source in front of a very small two slits or very two small pinholes separated by a distance of d. Then any incoherent sources will become a coherent sources because of the way they interfere or the way they interact with those particular pinholes, because these two individual pinholes will start to act as individual sources of light and hence they will be coherent in nature. After passing through that particular slits, the light sources will act as coherent sources and they will constructively and destructively interfere on the back of the screen. So again, which are acted as coherent sources, and bright fringes appear where constructive interference takes place, that is the central maximums, and dark fringes appear where destructive interference happens. That is, again, you saw there is bright and dark alternating spots that is being visible in the Young's double slit experiment. So the bright spots actually signifies what is known as bright fringes and the dark spots actually signifies dark fringes, which actually corresponds to the constructive and destructive interference which was happening at that particular point. And that is all about Young's double slit experiment. And just one condition about this particular experiment is that the central maxima and central minima should not change with respect to time. That is, the light sources should not radically change suddenly with respect to time. That is, the central maximum and central minimum should not move or change with respect to time as you're performing this particular experiment. So again, in order to achieve that, we have very small conditions, and those are So the conditions are basically that the two light sources must emit the same frequency. That is, if they are the monochromatic light sources which we are taking, then there is no problem. So again, the two light sources should emit the same frequency and they should be monochromatic. For example, a sodium vapor lamp emits somewhere in the yellow region, and if you are taking a laser light also, it also is a monochromatic source. Like that, you should choose a monochromatic source with the same frequency. And the next condition is that two light sources should be coherent, and the two slits will ensure that the two light sources will be coherent. And the final point is that amplitudes of these particular waves should be near equal or should be equal. That is because we want to get perfect interference patterns. That is why the amplitudes should be nearly equal. Otherwise, we will get a gradient spectrum rather than a clear cut result such as bright and dark fringes. So for that reason, the amplitudes should be very nearly or equal in nature. So the next topic is diffraction. So what exactly is diffraction? Basically, it is very similar to interference. No actual scientist can actually say that, okay, interference is this and diffraction is this, because both are very similar and it is very hard to differentiate them. So we can just try to, make a line between interference and diffraction. So diffraction can actually be explained as the bending or spreading out of light when it encounters obstacles or very narrow slits. That is, when light is passing through, let's say this particular light is passing through like this, and when it reaches an obstacle or a very small slit, what happens is that light actually spreads out in all particular directions, which will actually produce diffraction patterns, which is very similar to interference pattern. The only difference is that interference has very specific parameters. For example, two light sources. Here it is not like that, and hence the pattern produced also will be slightly different. Yes, it is combination of bright and dark fringes only, but there is a slight difference in the way these patterns are actually formed. That we will discuss as a comparison between diffraction and interference. That will be enough for your examination. So again, the difference between interference and diffraction, or interference and diffraction, is just that, okay, interference is produced mainly because of two particular light sources, while diffraction is produced by a large incoherent source, generally speaking. Or you can also say that due to multiple sources lying on the same slit, that is, if sun is there, if there are many tube lights in one particular hall, or many lights from other halls and headlights and many other natural light sources are all projecting light onto just one single slit, then you can say that, okay, the pattern you observe is actually a diffraction pattern. You can actually see this as an aura line around the sun or the moon or many stars also. That actually refers to as a diffraction pattern or a diffraction grating pattern. And when we come to interference, all the bright and dark fringes are of same intensity, or just simply saying, we can say that all the bright fringes are of same intensity. But when it comes to diffraction pattern, the central most pattern that is observed, or the central maximum, will have twice the width of the very next maximum. That is, the secondary maximum will be half the thickness of the central maximum, which means that at the very center it will be producing a very large pattern, and as we move to the sides it actually slowly diminishes in size and slowly disappears. And in interference, we can say that all the bright and dark fringes are of the same width. That is, again, they are of the same width and same intensity. But when we come to diffraction pattern, we can say that intensity of the bright fringe decreases as we move left or right from the central maximum. So like I said earlier, the size will be the double, and as we move away from the central maximum, it slowly decreases in intensity and perishes away. So that happens. And the width of the central fringe is actually twice as that of the secondary maximums. So that is the main difference between diffraction and interference. But again, basically they are very same and very hard to differentiate. And if you can differentiate them, this would be a very good way to differentiate interference and diffraction. So the last topic is polarization. So what exactly is polarization, or specifically what is unpolarized light and what is polarized light? So we know that light is now behaving like a wave. Like light is behaving like a wave, but is it just one singular wave? No. If I say this is a red color wave, it means that it is somewhere in the visible light spectrum or somewhere in the infrared spectrum. It is not just one ray of light or one wavelength of light that is passing through the universe or passing into our homes like this. It is actually a spectrum of radiation that is coming towards us at different wavelengths and different frequencies. So this type of waves or these type of rays of light is known as unpolarized light. Or to be more specific, we can actually say that light having electric field oscillations in every particular direction is known as unpolarized light. Again, you know that waves are produced because of charged particles oscillating up or down, and perpendicular to those oscillations, waves are being produced, which means that the electric field component is actually dominating in that particular wave, and the magnetic field component is actually very less but still exists. So we call it the visible light, or simply the light or the radiation which is carrying light, as electric field vector or electric vector. So in that particular sense, we can say that, okay, all optical phenomena are because of this electrical vector or electrical interference. And then we can say that if those vibrations, that is, if this is a particle of light, then if the electric field vibrations are in all particular directions, then we can say that that particular light is unpolarized light. So what will be polarized light? Quite the opposite. That is, when the electric field oscillations are restricted towards entirely in one plane, then we can say that, okay, that is polarized light. So again, unpolarized means electric field oscillations in every particular direction, and polarized light means electric field oscillations restricted to just one plane only. So again, we'll deal with what is polarization, what is unpolarized light, and how can you polarize light, and what are the specialities of polarized light in the very next session. And today this is all about polarization for now. So again, we have discussed many things here today, and we'll discuss more things in the very next session. Until then, thank you.